Hi, I'm Lei. Very exciting to talk here. And I'm co-founder and CTO for LanceDB. And this company, we build Lance format and LanceDB on top of it. And also, we are very excited to be like one of the smaller pieces in Extra to help them to compete with Google. So for Lance, we have been building this for almost 3 years, and in the beginning, that's actually, we started this company before ChatGPT was a thing. We are building this company for autonomous driving cars. So many of the design principles at that time, we try to help the self-driving cars to accelerate their development cycles. However, just realize that this thing apply to a lot of different AI companies throughout the year. That's why we have a very wide adoptions out there. Right? For today, for Netflix, Uber, Huawei, and many of the frontier labs out there are actually using us for a different purpose. Right? For example, Huawei is using for racks, and Exa using us for the data curation, just download the whole internet. And for WordLab and Runway and Luma, they are using us to store the videos and images to train their generative models out there. Right? Today, we have more than exabytes of data out there. That's another line that we match to today's thing. We support exabyte of data from all those companies combined. So what's the difference between why we need to build a new types of data infrastructure to support those kind of data, right? At 4 years ago, when we started to build those infrastructure for self-driving cars, at that time, what do we have at hand? We have Iceberg, we have Parquet, we have JSON file, we have HD file, right? And all of them was designed for last generation of the infrastructures that does not match to, at that time, what we need for the workload that we need from this very large scale petabytes of data. For us, at that time, what we need is we can do very fast training. We need very fast shufflings. We need serving the data over petabytes of images and frames under 1 second, right? And we want to be able to replay certain sequence between the projection and the prediction and all the sensor data along together. And at that time, we don't see any single systems physically can support those workloads. So we basically sit down to think what kind of system need to be designed for those kind of workload, right? So at that time, we spent years to build system around existing big data infrastructure that for the company, we want to spend most of the time to do research on the models. However, from the AI research themselves to infrastructure guy like me, we spend a majority of our time is just to try to piece different technology all together, just make things barely work at that time, right? So the main disparity between the things we need to the traditional big data infrastructure is big data infrastructure was designed for those integers, numbers, strings, and they want to run aggregations on those data and have this building BI report, right? However, for us, we need to understand sensors, prompts, tensors, images, videos in very interactive ways. So this is where the disparity comes from. So that's why we want to build a new type of systems. So before LanceDB was a thing, at those companies, including Cruise that I work for, we will have one single data lake from the last generation. For example, Iceberg data lake, or even just a bunch of Parquet files, and ETL these files into each of individual data silos. For example, we can put all the driver nodes into Elasticsearch for search, and put clip embeddings into vector database for data minings. And then we put data into machine, TF record or other kind of formats just for training purpose. Right? However, as infrastructure lead at that time, we need to support ETL of 11 different pipelines, and all the pipelines are constantly failing every single day. Right? The life is pretty miserable at that time. So that's why I want to actually build one system. When you dump the data into this system, you can run multiple different workloads all together within this system sufficiently. That's the design principle for LanceDB. So once you have one system can support different type of workload, we will actually have much simple view of the data. You have one single source of truth, however, to support from, say, scan to queries to search to like vector search or even full text search at the different stages. And this also prevent you to have multiple slightly different data silos everywhere and become dark eventually, and you don't actually know the transform whether it's right or not between each of the data silos. So to enable that, we pull back a little bit. 3 years ago, we examined all the tooling available out there, and think that we should start to build a new data foundations to support these visions. And that time, we think this thing, we basically rebuilt a new columnar format that is from scratch. It's similar to where, say, Parquet ORC or Iceberg Data Lake is today. However, the main difference here is like we are not only a file format like Parquet or ORC, we also are lake format or table format like Iceberg or Data Lake. These very tight integrations altogether are controversial as 3 years ago. However, it enables us to do optimization across the stack very easily within the very small team. And I think most significant feature that deviates us from traditional lake format is like, first thing, we are columnar format. However, we support constant time random access within the whole dataset itself. The second thing is like, and this is actually the feature that Exa is using. We call that two-dimensional storage. Zero copy data evolution means that once you add a new column or update a new column, does not need to rewrite your data set, right? And everything else is built around these two distinguished features, right? Especially people know us as a vector database, but a vector database itself is basically because of very fast random access, it's very easy for us to build any arbitrary types of random index to point back to the data itself. So every index is basically a key value to a pointer to the data itself, right? As long as we have very fast random access, we can enable different types of search behaviors. So as you can see from our majority of the users, they are using this either for the surfing, online surfing itself, to build racks and build recommendation systems, or put this into machine learning training pipeline from the beginning of accurate data as Exa and many other companies do, until to the point that they use this for the training and do feature engineering. So the first most controversial features we had 3 years ago is to support very fast random access on a columnar format. At that time, people think that columnar format and random access should be two separate markets. However, we just realized that means we need two copies of 50 petabytes of data for a cruise, so we cannot afford that. Then we think we want to actually achieve the goal that within this whole data set, no matter a few billions of rows you have, we want at most 2 IOs to read any single data point within the data set itself. And no matter how nasty your nested structure, how deep the structure is, we only need 2 IOs to read any given data. The way we do that, as you know that our data buffer is built on top of Apache Arrow, so they have multiple buffers all together to glue together to present new abilities and a bunch of other like offset and all other types of data within it. The solution we have is using something called mini buffers. that we put all bunch of different bitmap and real data all together, convert that into a buffer, and the size of this buffer match to object store or your local NVMe's I/O size means that anything smaller than that size, you don't have more advantage or faster latency to read through those data. So this is a basic unit for us to be able to read one chunk of data within just one single I/O over S3. So another thing very controversial is if you are familiar with Parquet or ORC design, they will group the data into row groups. So you can align each different columns with the certain rows. However, we realize that because we store the disparity of a data size within our storage is so big, we store from booleans to YouTube videos, right? From 1 bit to 20 gigabytes. It's very hard for them to align together within the memory before you flash that out. So the traditional row group, this is actually our first design, is that we either out of memory flashing those large blobs of data, or each group is so small that when you scan over the data, you don't have enough sequential scan to actually read through those smaller integer or Boolean data for fast aggregations. The way we do that is no more row groups. So we will flash the data at different paces. From a large blob, we'll flash much faster, where Booleans we can accumulate like millions of Boolean values before we flash once, right? That means once you have this SQL scan operations over these Boolean features, we can use one I/O to read a few millions. And it's very fast for when we integrate it with, say, Trino or Spark to run analytics queries. And 3 years ago, when we say that we want to provide randomness to read any single cell within the data, it's controversial in the way that people think that once you have a very good compressions, you will have read amplification that defeat the purpose of random access, right? However, we have done a lot of work to support compression without losing the random access performance. You can see here in many different data set and different data types, we are actually smaller than Parquet. And in the meantime, we have 100 times faster than Parquet in terms of random access. So our latest dataset version called Lance 2.2, which on those AI dataset is significantly smaller than Parquet, even Parquet using Snappy to compared to using Snappy to compress those Parquet dataset. So another thing that is very different from traditional big data infrastructure is that if you are familiar with, say, Parquet or ORC, they are the spec of a data format. And there are many of different implementations of those specs. Some are in C++, Rust, or Java. For Lance itself, we only have one single implementation in Rust, and we change the query plan. We actually implement the query plan within the format itself. The query plan is rewritten in the way that we understand that there are very large blobs underneath on the S3, so we will reorder the I/O, be able to reduce the number of the reads against those large blobs. For example, if there's a query that you will read, for example, you want to span a prompt and image columns from these tables. In traditional Spark or Trino, you actually need to read these whole columns of images all together and do the filters within the memory, then do the limitations here. But for us, we repurpose, change that. We read the index first, and when we actually read the image and prompt column, at this time, we only have 10 I/O left to read the final results. And another thing is different. It's interesting for us. It's like 3 years ago we are one of the first vendors that actually building all the index in from object store itself. Right? We assume that all the index will touch the object store first before we can serve to our customers. That assumption limits how much we can do if compared to you assume the data is on disk. For example, we cannot do mmap, we cannot update in place. So everything is designed differently. However, today we do have a very rich level of different indexes. We have say different vector database, vector indexes, AVIPQ, RQ, RabbitQ, and HNSW. And we also have full text search, JSON, and even GeoIndex contributed by the communities. Right? The nice thing about this is like every index we have is a secondary index. It means that we have a main table somewhere, and all the index are the file as a key value pointer point back to the data. It's very easy for the community to contribute different types of index or even customize that for their own purpose. And this is a feature that actually where Exa and many of our customers come to us for. We call this zero cost data evolutions. Means that, for example, if you take a look of this, the sequence of this data set, in the version 1, we will generate a data with one column, and the second version, we append some data within the same column to it. However, the third operation is adding new values to the existing data set. And this new value will generate two separate files that represent this single column alone without rewriting the full data set. This is particularly more interesting in a way that if you assume this is for a self-driving car company, right? Or I already have 50 petabytes of data. Once we want to add one Boolean column for whether I have, say, old nanny cross the street and with a red light on the right side of the image, I don't want for this one single Boolean column to rewrite 50 petabytes of data. And this is how things can actually work very efficiently in terms of storage and compute. And this is actually the most beloved features for LanceDB today. Also, we do provide very simple API from our Python SDK. It's just define a Python function, then add into a column, then we'll compute that column for you and do the commits. So many of our customers out there, for example, World Labs and Runway, Midjourney, they all comes to here. Actually, Exa might be similar, but for example, they do have one data set that has one single columns and run different jobs to adding different features all in a parallel at the same time. And those parallel jobs will contiguously commit each column at different times. And our distributed transaction model can actually handle all the incremental commits between different users and different jobs easily here. So we are currently at a stage that people are using us in very large production data set. And our largest data set is on like hundreds of billion rows scale. And we are trying to push to trillions of rows scale. I think this is very unique to us in a way that because we are the storage engine that not only need to manage the table format scalability, also need to manage the index, be able to keep up with the same scale, with a very high ingestion rate and a very high updates rate, and all the same QPS. So we need to improve this from two different angles. And we do have some ongoing work from the open source to address that in both ways. So our commercial as a company, we do have a commercial product built on top of open source LanceDB and Lance format itself. So our commercial product is called Multimodal Lakehouse. It means that we not only store the data, we help you to basically manage the computations of the features, and from the beginning to the end. It's very similar to the DAG that we present before this talk. So basically, every new features is a declaratively a Python function that we will do backfills, preemptions, checkpoint, and partial commit for you, and it's managed by, orchestrated by the LanceDB commercial product here. And we do have a very large installation out there. It's almost close to 1 million cores and a bunch of GPUs out there. Okay, I think that's all I have. And also, we are also very actively hiring. Please connect to me. And this is our open source Discord. You can join that.